also I did some other work, which is the orange box there. The work I'm going to talk to you about today has been published in eJAW, so that was a very good result. The other paper is still under review. Now that work has been based on some work I did in 2005 and 6. So this work is very much a continuation of that. So this is about railways and their capacity. So this is a topic that is still very much, is a big field. There's a lot of research going on. It's a very important task. Railways are very important in our society, in our cities, to move people around, passengers and freight. And the demand for those is still increasing. Now, if you say, I want to determine the capacity of a railway system, that's not an easy task. It's actually quite controversial, and there's many different approaches. So the main thing that I have addressed is the lack of kind of modelling of competition within the railway system. So most of the other approaches are not really concentrating on that. They're just working out some measure of operational capacity. But on railways, trains are not all the same. Some are passenger, some are freight. And what they do, what they transport is not the same. So they actually compete for infrastructure. And some trains are actually owned by different companies. So in essence, the access to the railway is competitive. So if you're going to determine the capacity of the system, you have to take that, those competitive aspects into account. So that's what this paper, this work is about. So the two main questions that people ask when talking about railway capacity is, can the network handle an intended traffic flow? And is there sufficient capacity for additional trains? And what people would like is a transparent way to define, kind of understand capacity. You want an approach which is easy to understand and to apply. And a capacity analysis also identifies how the system can be used. So it's not just a single value, it's kind of like a plan as well. So the capacity is like a number of trains that you move through the system, and it's also a mix of trains. So how many of each of the different types of trains do you put through? So my viewpoint on capacity is we're actually working at what's called absolute capacity. Now, absolute capacity is an upper bound on operational capacity. Other people have called it different things. Absolute is pretty much my name for it. So this form of capacity is an ideal level, and it looks at really kind of saturating critical sections of the network and then counting how many trains you can actually put through the system. So it intentionally ignores things like delays and interaction effects and any other type of stochastic type factors. And it also ignores some operational kind of procedures that affect capacity. Now the reason I've done that is because for every one of those different factors and variations, you get a different capacity of the system. So what you'd like is a more stable kind of measure, which is kind of a reference point for other types of techniques. So in my belief, you need two types of capacity. You need a measure of operational capacity, and you need a measure of absolute capacity. And by comparing both of those two things, you can kind of identify if you can improve the system or not, for example. So as your absolute capacity, well, if your operational capacity is very close to your absolute capacity, then you know you're operating very, very well, and that the system cannot be improved by changing some operational factors. So in order to improve the system, you'd have to expand the system by duplicating some tracks or adding signals or something like that. But if there is a big difference, then you can actually improve the way you operate on that system, and hopefully then you will increase your operational capacity towards that upper bound. So the upper bound is a structural analysis. It's analysis of the properties of the actual physical layout of the system. So the model I developed in 2006 was an optimization model. So that was quite novel at the time because prior approaches did not do that. They were based upon developing, specific equations to measure certain attributes of the system. So what I did was actually said, well, let's leave it to the optimization model to determine the capacity. So all I have to do is add in constraints, technical constraints of how trains move and the sections and the layouts. And then the model will actually choose the maximum number of trains it can put through based on those constraints. So that was a good model, but the problem was it provides only a single answer. So you define some proportional mix of trains that you want to use the system. And given that proportional mix, the model will then tell you how many actual trains of each type can be put through the system. And so what I actually also proposed was a kind of process where you actually suggest mixes, solve the model, and then look at the answer, and then say, well, is that acceptable or not? If it's not, go and change the percentage mix and then run it again, and kind of do this kind of iterative process. So the main problem here really is that that's not representative of all possibilities, and the mix can change from day to day, from time to time. So you want to have some type of sensitive analysis of capacity. Now, you cannot enumerate all possible mixes and evaluate all possible mixes. There's just too many. So a better approach is a multi-objective framework, and that can cope with that concept. So I've developed a comprehensive set of multi-objective models. And what those models do is it determines the most equitable solution according to a clearly defined set of competing objectives. And this approach is also for the case where you have different types of capacity metrics. So it's not just, for example, in terms of the number of trains, but maybe perhaps the value of what is moved, or the number of containers that are moved on the trains, or the amount of freight, or some other type of measure of capacity. So you can actually mix all of those capacity metrics into one model and determine what the capacity actually is and costs. So these are the different types of competition that I considered. So we've got train type versus train type. Okay, so you might have, an 80 kilometre an hour train competing with a 60 kilometre an hour train, or 120, or some other type of train type. Now each of those train types are, either a passenger type or a freight type. So you can actually determine the capacity in terms of, balancing the competition between those two types. So do you have more passenger trains or more freight trains? How do you actually balance those two categories? You can also have competitions between different corridors. So where you have corridors which overlap with other corridors, then you have a set of sections which are common to both. So if you don't regulate the competition on those sections, then how you regulate, I should say, the competition in those sections affects the capacity quite significantly. There are other types of groupings. I won't actually go into those, but an interesting one is capacity expansion versus spending. So can you expand the system, and how should you expand it based on whatever cost and economic parameters you've got to take into account. So ideally, you would want to get the biggest increase in capacity without actually spending anything. But in fact, that's the opposite of that. What happens? You have to spend money to increase it. So you're looking for a trade-off there between those two different competing metrics. And also, you've got different capacity metrics which can compete against each other. So you want to maximize the number of trains, but also simultaneously maximize the value of, for example, the freight that you're moving, something like that. So in fact, increasing the number of trains may not actually do that for that objective. So those competitions are translated into the following objective functions. So in this case, these are are simultaneously being optimized. So for example, in the first one, in the pink box, you're simultaneously maximizing the number of passenger trains and also maximizing simultaneously the number of freight trains. So the original capacity model is actually quite straightforward. But the main part that actually does the capacity kind of limitation part is this equation, which is actually looking at each section of the network. So what you're actually doing is determining the occupancy of each section. That's the left-hand side of the first box. So you're working out the total number of trains that use that section and multiplying it by the time that they occupy the section. And that's the total time that that section actually occupied. And that must be less than or equal to the time, the duration of your time period multiplied by the number of sections, parallel sections. And in the orange box is the equations which link the number of trains that use the section with the number that travel between on each of the corridors. So the main decision variable is not the y, it's the x. That's what you're determining, that's the plan. So in this case, it's the number of trains of type I which are used on corridor C. So those trains can traverse the entire corridor in that time period. And the arrow above the variables is the direction of travel. So you have two directions on any section. So for every corridor, you've actually got to have a list of the sections which are part of that corridor. And then you have to sum up all the x's for all the corridors C to actually work out what's happening on each of the sections. So the other constraints of the model are to do with the mix of the different trains. So there's probably 3 or 4 different other equations, so you've got different types of mixes that you can specify. And that's pretty much it. So this model can be solved instantly, so it's not NP hard. I mean, it's an approximation, it makes some assumptions, but it's a high level kind of upper bound, as I said. So the new work is multi-objective. So apart from those equations and things, now we have multiple objective functions. So you might have 2, 3, there's no limit. So typically you might have, I looked at problems with 4 train types, 6 corridors. So 4 objectives, 6 objectives. And then I looked at a case where every train type on every corridor is a type of entity which is competing. So that's 24 objectives. So this is a little bit of multi-objective theory. I'm not sure if most of the group is aware of this theory and knows it. So the idea is that in normal optimization problems you have a decision space, and for every solution in the decision space you actually have an equivalent point in the objective space. So there's a mapping. So multi-objective theory is looking at the objective space, and what you want to do is find the boundary of the objective space, which is called the Pareto frontier. And every point on the Pareto frontier is either an optimal solution or a weakly optimal solution. So an optimal solution cannot be improved without deteriorating one of the other objective function values. A weakly optimal solution also exists on the frontier, but you can actually find other points on the frontier which actually do better. So the Pareto optimal solutions are non-dominated because you cannot find another solution which is better in all of the objectives. Now the idea is to find the solution on the Pareto frontier which is closest to some ideal point, which is called the utopia point. So the utopia point is kind of the jackpot solution where all of the objectives have been optimized, but rarely does it actually happen. Now, if you had the Pareto frontier, you can actually preference the objectives in different ways. So if you're clients actually want to kind of weight one objective more than the other, then you can actually move along the Pareto frontier. And that changes your distance metric. And by distance metric, I mean the measure that you use to relate your solutions on the Pareto frontier to that utopia point. So to solve multi-objective problems, there are a variety of different techniques. These are just three that I looked at. ECM is the epsilon constraint method. It's probably one of the best ones for a variety of reasons. Weighted sum method, the WSM one, is similar to what a lot of people kind of, you weight the objectives in a certain way. But what happens is that that method has a few flaws. It actually doesn't describe the entire Pareto frontier. It gets stuck. It kind of picks out certain points only and refuses to find the other points. So you need to do some type of adaptive kind of strategy to actually make it work. But the literature says it's not really very good. And I've tested that, and it's very much true. ECM is a very good technique, but it has some problems when you go into multi-objective problems. So it's really good on bi-objective problems. But as soon as your number of dimensions increases, then it has a number of weaknesses. So that's why you would then go to something like an adaptive ECM. Or there's another version called augmented ECM, and there's another one called lexicographic ECM. So the ECM method is really just a repeated solution of a particular type of optimization problem. So you choose one of your objective functions to maximize, in this case, and then you solve the problem and you put bounds on the other objective function values. So by changing this epsilon j value, you can work out the entire Pareto frontier. So there are no real rules about how you do that. In this case, you have a lower and upper bound for each objective, so you can actually move across each dimension by a certain increment and resolve the problem. And that gives you all the points in the Pareto frontier. So the x in x part is actually where your equations of your normal model actually lie. So in fact, that's just a kind of broad statement of, tens and thousands of possible constraints you can put in there. So the problem with ECM is that you have a state space explosion. So to actually apply ECM, you have to generate a hypercube, hypergrid, where you have this grid, and you have to split each dimension into so many points. So when you multiply out all of those number of grids, it just blows up. So it's into you can see that term there. So if you've got 24 objectives and you've only got 5 divisions in each dimension, you've got 1 by 10 to some ridiculous number of possible points to actually solve. So it's just not possible. I tried it on a 6 objective problem. It took 2 days. 100,000 solves were required. Now, it was pretty stupid because I didn't know that would be the case. I was new to this area. But I did it. And Cplex does cope. You can run Cplex 2 days and run 100,000 different model solves and collect all the results. But I certainly wouldn't suggest you do that. So that then forced me to look at an adaptive ECM. So I observed that infeasible points occur closest to utopia point in that hypergrid. So if you start from the 0 point, then you can evaluate all the points that are feasible. And when you hit an infeasible point, then you don't move off in that direction. So I have a theorem which says that for the capacity model of mine, that once you become infeasible, that you cannot restore it to feasibility, which then means that that is a good thing to do, and that you shouldn't keep branching off from that point. So this is a demonstration, well, a diagram of expansion in a 2D setting and then in a 3D. So I have written code in Cplex to do this. So the black point is where you start, and then you generate 2 points off, and then you solve the model twice. And then from each of those points, you generate another bunch of points. So you've got 3, and then you solve these 3, which then go to black, and then you project off again. So you keep expanding outwards. In 3D, it looks like this. So once you've actually got the Pareto frontier, you can do an analysis of the actual points and then choose a solution which gives you the best trade-off. So you normalize the value, so that is done on the left in the pink box, and then you evaluate the distance between that point and the utopia point using like a Euclidean distance formula, but there are other types of formulas you can use. So I implemented all of this in iLog Cplex, or OPL Studio as it's normally called. I could have done this in, say, C++ or C# or something else, but the scripting function is actually very good. So you don't have to worry about integrating your programming language with Cplex. That's the idea. Cplex provides basically a C++-like language where you just code normally. It does all the things pretty much any programming language does. You have arrays, dynamic structures. You can even do recursive functions, which is really good. I actually use that too in this code. Performance is very good. The only problem really is it doesn't have some types of data structures that you can have in normal programming languages. But you can get around that doing some other tricks. So this is typically what the code would look like. So I define some functions to do, say, the WSM method, the ECM method. And then I have just the main program code here where I set up my model. I generate the model. I call Cplex to solve it, and output some results. So this is actually working out some upper bounds for the ECM part. This is actually where the ECM is actually done there. So I actually haven't shown details. I've omitted the code. So all of those statements where you set up the model are all standard. So a lot of you will be familiar with some of those. So I applied these models to the case study of my earlier paper, which looks like this. It's basically a simplified version of the Brisbane network in some ways. So the Brisbane network has 4 or 5 main corridors, and they kind of meet in the middle. So I've solved a 2D, 4D, 6D, and 24 dimension problem. I've got the following 4 train types. That's their speed in kilometers per hour. So for the first one, I'm regulating the competition between the 4 train types. So I looked at 20 divisions, and that results in 8,000 points. So that's 8,000 model cells you would have to do to generate the Pareto frontier if you don't do any type of adaptive kind of improvements. And of those 8,000, only 1,768 were actually feasible. So there's a lot of work that just isn't necessary. But you can do 8,000 solves in 30 minutes on Cplex. So in this case, it's not a big deal. So the optimal solution says that you should have around 85 trains of type 1, 112 of type 2, 140 type 3, about 169 of type 4. So overall, the capacity of the system is about 506 trains in the time period that I selected. So the actual best solution is the 5,895th one of the 8,000. And that mix gives us an equivalent proportional mix. So 16.67% of the trains are type 1, 22.2 for the next one, and so forth. So this is actually quite a very interesting solution because it's actually linearly increasing. There's actually a theoretical property here for this train type competition problem. Now the reason for that is that the section running times of the trains are actually based upon a formula. So there is actually a link between the different train types. So hence there is a theoretical result here. But if you're using real data about real trains, this would not be the case. For example, if you were looking at, say, the average time for a train to move across a section or across a corridor, because the real times take into account lots of different things like gradient, curvature, temperature, age of the train, all sorts of things. So I'm going to show you some really interesting charts now. So when you solve these multi-objective problems, everything is good if you've got 2 or 3 dimensions. You can plot those and look at the Pareto frontier. But when you get into the higher dimensions, you don't really know, there's no way to actually visualize a Pareto frontier. So I have had to be a little bit more innovative here to actually try and come up with a way of looking at that. So I've got some charts here which are have some very unusual shapes. So this one has on the x-axis the 8,000 solution points, and then we've got the equivalent capacity for each of those points. So you have this very interesting kind of delta shape. This one is particularly interesting. I call this the rocket diagram for obvious reasons. Very, very unique shape, the way it kind of, at the back there. It has one solution, and it's symmetrical around the best. So this one has a theoretical result. You can see it. And it's got some interesting patterns in between. So again, another interesting chart. This one's solution point versus Euclidean distance. Now, with the adaptive ECM, it generates the grid in a different way. So it has a different number of points which have been evaluated, and the order in which it visits those points is different. So hence you get a very different shape coming off. So you get this one, which is different to the other ones. Again, I don't know what this all means. If you've got any ideas, I'd be interested to know or discuss it with you. Again, this is quite interesting too. So that's the 4 train competition problem. So now moving on to a bigger problem, the 6 corridor one. More dimensions means that you have to have less divisions because of the state space explosion. So this is a case where you have 100,000 points, but only 5,000 of them are actually feasible. So with 10 divisions, there were 2 solutions which were best, but if I could go to more divisions, then maybe there is a single solution which is best. So I don't really know. So the conclusion here is that 10 divisions is too few. So this is about the 6 corridors competing for resources. So the 2 solutions are shown there. That's the number of trains which use each of those 6 corridors. So overall, the absolute capacity is 612 trains, and corridor 1 and 5 are most utilised. So ECM took 2 days, but the adaptive one took 1 hour, which made me much, much happier. So the charts for this case, still interesting, but not quite as, the pattern's not quite as obvious. The adaptive ECM gives you more interesting charts. So the next problem I looked at is the capacity expansion problem, where you're minimizing cost of those expansions. So I looked at the case where I'm duplicating sections of track to actually increase capacity. So it's only a bi-objective, so I could do a lot more divisions. So I could do 100 divisions, and the best solution on the Pareto frontier says that I can increase the capacity to 1,365 trains with a cost of 2,711. So that's a scale value. It's millions and billions. Now, the system, I should point out, has a capacity of 675 trains without actually doing any type of expansion. So the expansion activities only increase it from that value up to the 1,365. So what's interesting about this result is that you have a 29% of your budget you're spending to get an improvement of, I think it's 60 or 70% of the way along in terms of the absolute capacity increase. So that's the Pareto frontier. So here you can see that with no spending, the capacity is at 675. Now the utopia point, the ideal point is obviously getting to this upper bound with no spending, which is not possible. So as you spend more money, your capacity increases. Now it's moving up in different, I mean it's not linear, and it's, you know, some parts are quite shallow, some parts are actually vertical, some parts are horizontal. So any one of those points on that frontier is a good solution, but the idea is to actually get close to this ideal point. So it turns out this point here, this area here, is roughly the best. You get the best trade-off between spending and increasing capacity. This part here is quite noticeable. It means that as you spend money, you don't actually get an increase, so it's not a good use of spending. So if you take an arc through here, there's actually quite a few solutions which are quite comparable along here. And these are the Euclidean distances associated with that Pareto frontier. So as I was saying, you've got a number of solutions down here which are at the same type of distance from the utopia point. So this chart actually does the same analysis, but it puts limitations on the duplications of the different sections of rail. So for example, in real life, the network there's not often space enough to put like 10 additional parallel tracks. You've got some limitation. So if you do a sensitivity of that limitation, then you get different Pareto frontiers. And as you can see here, you get these bottlenecks which you reach, and then you get no increase in capacity. And as you relax the limit, your capacity then increases further. So the last problem I actually solved was the biggest one, which is a 24 objective optimization problem. This is where the case you have corridors and trains grouped together as categories, and each of those corridor and train groupings competes with all the other ones. So because there's 24 objectives, I could only do, say, 5 divisions. As you can see, that's a huge number of points. So basically, without some better adaptive ECM approach, you cannot work out the Pareto frontier for this problem in an efficient way. So I didn't do it. So what I did instead was I looked for the best solution, so that best point on the Pareto frontier. So that is equivalent to solving an optimization problem with the Euclidean distance metric as the objective only. Now that problem then becomes nonlinear. So to actually solve this, I apply two different approaches. But this is the solution that you get. So the solution gives priority to 4 of the corridors out of the 6 and to 3 of the train types. Some of the train and corridor pairings are zeroed, so you don't actually have any trains on those. And when you actually go back and look at those ones, it makes sense because they have, those corridors are too long and the trains are too slow, so then why bother putting many of those? So to increase your capacity the most, but also equitably kind of assigning out those numbers of trains, it's actually better to assign trains to these train type and corridor pairings. So the idea here is not to actually choose the best train type. You're balancing all the train types and providing a solution that is equitable. So I applied a hybrid simulated annealing algorithm to solve the problem initially. So this identifies the optimal solution only. There's a dedicated improvement phase which has been added to make the algorithm very efficient. The objective is the Euclidean distance, and there's a perturbation operation which is random. So this is a continuous problem, not a discrete problem. And because it's continuous, you need to choose the perturbation amount. So most other approaches with simulated annealing for that continuous type of problem has a fixed, static kind of perturbation amount, but that is not very good for this type of problem. So I have a value which changes as the algorithm proceeds. So as the temperature in simulated annealing decreases, you also decrease the perturbation amount. So in this case, I start off quite coarse at 17, and as the temperature drops towards 0, the final value is 0.00003. So you're only making little moves on the solution. So you're getting that kind of fine-grained search capability that you need. So I didn't do anything particularly special with the algorithm or the algorithm's parameters. I started with a temperature of 100, dropped down to 0.1, and the temperature reduction factor is 0.99. But I did run a lot of iterations within each step of simulated annealing, so I did 1,000. I started from either the 0 point, so that's where every part of the solution has a 0 value, or I moved it further along. So the first one, the 0 case, you're quite a long way from the utopia point. So it means you have to do more work to actually get to the optimal. But both worked quite well, and I was actually able to show that the simulated annealing solutions were actually basically getting the optimal solutions because I had already solved the optimal ones for the other reduced problems. So the other approach, though, I applied was separable programming. So simulated annealing is very good, particularly if you've got hundreds of objectives or something, but it doesn't guarantee that you know what the actual optimal solution is. And where you've got some type of theoretical result, it's actually not going to find it. So I use separable programming instead. So you can use that approach to linearize the Euclidean distance metric. Then you bypass nonlinear optimization software and approaches. So the approach I took is actually different to the standard approach which is used in the Winston textbook and anywhere else that you actually care to look. So the original separable programming approach is based on adjacency conditions and special ordered sets and things. So the reason I didn't use that one for 2 reasons. I didn't know how to implement that in Cplex. Probably can, but I didn't have time. But more importantly, the different types of objective functions worried me a bit. So you had a mixture of maximization and minimization ones. So the original separable programming is based upon certain issues of convexity. So I wasn't sure if that was going to hold if I had combinations of maxes and mins and so forth. So I just generated a more generic separable programming approach. So I rewrote the objective function. So it's the sum of these square terms, and each of those square terms can be approximated by a piecewise linear function. And the square term is very easy to split up. You don't need a lot of points to actually get a very good approximation. So I actually looked at points up to around 200, but points of, divisions of about 100 is fine. And you get very little change in solution. In fact, you can use 25, that's good enough too. So to do this, you need additional binary decision variables to be added. You need to add in some constraints where you're multiplying those binaries with continuous decision variables. Now that would normally be a problem, but fortunately there is some tricks that allow you to linearize that too. So hence that's why this approach is successful. So this is the beast that results. So in essence, what you're doing is actually choosing which interval you're going to, on that piecewise linear function that your solution will be at. And then you have a parameter which says within that interval where along the line you're going to be. So then we have some equations. That's that part here. This part here is just defining what these two terms are. This equation here is working out the normalization of the objective function values. And all the magic is happening in here. That's with the linearization of the product of a binary and a continuous variable. And these equations here are just kind of telling you where along the line your solution is going to be. So I did a sensitivity, and as I said, 100 points is fine, but 200 or more, it just dies. CPlex just can't cope. So it would be interesting to apply the normal separable programming approach to see whether that would be better or not. So in conclusion, the approach has been successful. It does a very good sensitivity analysis of the capacity for a wide range of parametric values. A C++ implementation is probably warranted if you're going to do more sophisticated adaptive ECM techniques and so forth. There's still lots of opportunity to do more efficient mesh generation. And recently I've discovered lexicographic and augmented ECM. So what they do is actually do more of a pre-stage analysis which reduces the bounds of each objective function. So the lower bound and the upper bound gets shrunk. So by doing that means that your hypergrid can have more points because the grid's actually smaller. So you get more precision and your Pareto frontier is more accurate. And that reduces the computing time too. So for example, 2 days for the full ECM, 1 hour for my adaptive one. I could do it probably in 5 minutes if I did augmented ECM, perhaps. So it's definitely worth doing. Okay, so that wraps up my talk. I'm happy to take questions.